Hey everyone, today we're going to be talking about the basic inverse trig derivatives. So, let's start this video by identifying what inverse trig derivatives we already know. So, as you can see, we actually haven't done any of them yet, but that's alright because in this video we're going to figure out the derivatives for the inverse sine of x, inverse cosine of x, inverse tangent of x, inverse cotangent of x, inverse secant of x, and the inverse cosecant of x. So you can also call these functions the arc trig functions. So you can call this the arc sine of x and the arc cosine of x, but I usually call them the inverse trig functions, but it really doesn't matter. Whatever you are familiar with is fine. And a quick note, in this video I use a lot of the derivatives that have been mentioned in my previous videos, and especially derivatives that were mentioned in my basic trig derivatives video. So if you're not sure about any of those derivatives, be sure to click the link in the I. Let's start our derivative process by talking about the derivative of the inverse sine of x. Now, as a quick refresher, when you're using inverse trig functions, the inside part, or the argument of your inverse trig function, is talking about the ratio between two sides of a triangle, and what the function is equal to is the angle. So in our case, the inverse sine of x is going to have an opposite side equal to x and a hypotenuse side equal to 1. From here, we can use the Pythagorean theorem to solve for the adjacent side, which gives us the square root of 1 minus x squared. And then finally, to set some angle, I just set our angle equal to y. Using this information, what we can do is set up an equation. So y is equal to the inverse sine of x. From here, we're going to solve for x and have that the sine of y is equal to x. Now we can take the derivative of both sides, and we'll have the cosine of y times dy over dx is equal to 1. This is because when you take the derivative of the sine of y, you have the cosine of y times the derivative of y, which in this case is dy over dx. You can also write this as y prime, or however notation you feel comfortable with, just as long as you remember to use the chain rule for this. From here, what we want to do is solve for dy over dx. So we're going to have dy over dx is equal to 1 over the cosine of y. From here, what we want to do is replace the cosine of y with something that is in terms of x. So the cosine of something is equal to an adjacent side over the hypotenuse side. So the cosine of y for our triangle is going to be equal to the square root of 1 minus x squared over 1. From here, we can just simplify and have that the cosine of y is equal to the square root of 1 minus x squared. And then replacing that with the cosine of y, we have that dy over dx is equal to 1 divided by the square root of 1 minus x squared. Now, let's talk about the derivative of the inverse cosine of x. So, our triangle is going to look like an adjacent side being equal to x and a hypotenuse side being equal to 1. From here, we can use, again, the Pythagorean theorem to solve for the opposite side, which is going to be equal to the square root of 1 minus x squared, and we can set some angle equal to y. From here, we'll set up an equation, so we'll have y is equal to the inverse cosine of x. From here, we can solve for x and get the cosine of y is equal to x, and take the derivative of both sides. What we're going to have is negative sine of y times dy over dx being equal to 1. What we're going to do here is solve for dy over dx and have dy over dx is equal to 1 over the negative sine of y, which is equal to negative 1 over the sine of y. You don't actually have to bring the negative sign to the top. You can leave it in the denominator. I usually just prefer to bring it to the top because it's easier for me to read, and I also like remember to do distributive properties with it if I need to, but it's whatever you're most comfortable with when writing out your answers. So again, what we need to do is figure out what the sine of something is equal to get our derivative in terms of x. So the sine of something is equal to the opposite side over the hypotenuse side, and the sine of y, using our triangle, is equal to the square root of 1 minus x squared divided by 1. In simplifying this, we get that the sine of y is equal to the square root of 1 minus x squared, and to bring that back into our derivative, we have dy over dx is equal to negative 1 over the square root of 1 minus x squared. Since we finished our first two inverse trig functions, let's talk about the derivative of the inverse tangent of x. So the argument of our inverse trig function is going to be talking about the ratio between an opposite and adjacent side. So on our triangle, we're going to have our opposite side being equal to x and our adjacent side being equal to 1. Using the Pythagorean theorem, we can solve for our hypotenuse side and find that it's equal to the square root of x squared plus 1. And from here, we can just set an angle, y, to bring things together and create an equation. So our equation is going to read y is equal to the inverse tangent of x. From here, what we want to do is isolate our x and get the tangent of y is equal to x, and then take the derivative of both sides. This is going to leave us with the secant squared of y times dy over dx equal to 1. What we want to do now is get our dy over dx by itself and have dy over dx is equal to 1 over the secant squared of y, which is equal to the cosine squared of y. Again, you don't have to actually write it as the cosine squared of y. You can leave it as 1 over the secant squared of y, but I prefer to use the primary trig functions just because I'm more comfortable using them, and I feel like I remember what they are with respect to the ratios of sides on a triangle. But if you feel like you can use the, secondary trig functions, then by all means, go for it. So from here, we know that the cosine is equal to the adjacent side divided by the hypotenuse side. So for our triangle, this is going to be the cosine of y being equal to 1 over the square root of x squared plus 1. And to bring things together, we have that dy over dx is equal to 1 over x squared plus 1. Let's now talk about the derivative of the inverse cotangent of x. So our argument is going to be equal to x, which means that we're going to be talking about the ratio between the adjacent and opposite side. So our adjacent side for our triangle is going to be equal to x, and our opposite side is going to be equal to 1. And using the Pythagorean theorem, we find that our hypotenuse side is equal to the square root of x squared plus 1, and our angle can just be equal to y. So let's set up an equation and have that y is equal to the inverse cotangent of x. And from here, we can solve for x and get that the cotangent of y is equal to x, and then take the derivative of both sides, giving us the negative cosecant squared of y times dy over dx is equal to 1. From here, we want to solve for dy over dx and get that dy over dx is equal to 1 over the negative cosecant squared of y, which can also be written as negative sine squared of y. Now, we know that the sine of something is equal to the opposite side divided by the hypotenuse, and the sine of y, using our triangle, will be equal to 1 over the square root of x squared plus 1. And from here, we can replace what we have in our derivative to say that dy over dx is equal to negative 1 divided by x squared plus 1. We've now derived 4 of our 6 inverse trig derivatives, but I've saved the hardest 2 for last, and those are the inverse secant and inverse cosecant of x. So let's start by finding out what the derivative of the inverse secant of x is. So the inverse secant is going to tell us that we're talking about the ratio between a hypotenuse and an adjacent side. And since it's x, we know using our triangle that the hypotenuse side will be equal to x and the adjacent side will be equal to 1. From here, we can use the Pythagorean theorem to solve for the opposite side, which is going to be the square root of x squared minus 1, and we'll have our angle, which we can set equal to y. We can create an equation and have that y is equal to the inverse secant of x, and then solve for x and have the secant of y being equal to x. Now, let's take the derivative of both sides and have the secant of y times the tangent of y times dy over dx is equal to 1. Let's solve for dy over dx and have it equal to 1 over the secant of y times the tangent of y. And what I'm going to do here is simplify a little bit. So dy over dx will be equal to the cosine of y divided by the sine of y divided by the cosine of y. This is because 1 over the secant of y is equal to the cosine of y, and the tangent of y can be written as the sine of y divided by the cosine of y. And simplifying even further, we have dy over dx is equal to the cosine squared of y divided by the sine of y. From here, we're going to replace our trig functions with functions with respect to x, which is going to be coming from the triangle that we have. So dy over dx will be equal to 1 over x and then squared, and then divided by the square root of x squared minus 1 divided by x. This will then be equal to x divided by x squared times the square root of x squared minus 1. But what we want to do is simplify a little bit more and have 1 over x times the square root of x squared minus 1. So if you're familiar with the derivative of the secant and the inverse secant and inverse cosecant, you might think that what I have is a little bit wrong or that I'm missing something. But what I'm going to do is actually show you what I'm missing and why we need to include it. So moving on to the next slide, we have a graph of the inverse secant of x being equal to y. So as you can see, the function is going to be increasing until it gets to about x equals -1, and then there's a region that it's undefined, and then after x equals 1, the function is then increasing again. So it's very important to note that I said increasing, and that is because we can say that the derivative or the rate of change or the tangent line is all positive. And I think I mentioned this in my what is a derivative video. A derivative can also be interpreted to be the slope of the tangent line of a graph. So since our function is always going to have a rate of change that is positive, we need to add absolute value signs to our x. And the reason we don't need to add it to the whole thing is because the 1 is going to be a constant, and the square root of x squared minus 1 will always be positive unless it's x is between -1 and 1, because then it'll be undefined. And that, you can see, is the derivative of the inverse secant of x. Let's finish things off by talking about the derivative of the inverse cosecant of x. So the inverse cosecant is telling us that we're talking about a ratio between the hypotenuse and the opposite side. So our triangle is going to have a hypotenuse equal to x and an opposite side equal to 1. And using the Pythagorean theorem, we can find that the adjacent side is equal to the square root of x squared minus 1 and have our angle being equal to y. We can then create an equation using this information and have y is equal to the inverse cosecant of x, and then solve for x and have the cosecant of y being equal to x. Taking the derivative of both sides, we get the negative cosecant of y times the cotangent of y times dy over dx is equal to 1. And then solving for dy over dx, we get it equal to 1 divided by the negative cosecant of y times the cotangent of y. We can simplify a little bit and find that 1 over the negative cosecant of y is equal to the negative sine of y, and the cotangent of y is equal to the cosine of y divided by the sine of y. And simplifying even further, we get that dy over dx is equal to negative sine squared of y divided by cosine of y. We can now replace our trig functions with our values from the triangle and have negative 1 over x squared divided by the square root of x squared minus 1 divided by x. And this is equal to negative x divided by x squared times the square root of x squared minus 1. And then we can drop our x's and have negative 1 divided by x times the square root of x squared minus 1. And just like with our inverse secant x, what we need to do is look at the graph of the inverse cosecant of x. And what we have is that the slope of the tangent line at any point other than between negative 1 and 1 is going to be negative. And this means that the derivative is always negative. So what we need to do is incorporate our absolute value signs into our x. And again, we can't do it around the whole thing because since our derivative is always negative, what we need to do is keep our negative 1, and we don't need to put it around the square root because it will always be positive unless it's between negative 1 and 1 for our x value, because then it'll be undefined. Let's recap all of the inverse trig derivatives that we found in this video. So to bring up our table, the derivative of the inverse sine of x is equal to 1 divided by the square root of 1 minus x squared. The derivative of the inverse cosine of x is equal to negative 1 divided by the square root of 1 minus x squared. The derivative of the inverse tangent of x is equal to 1 divided by x squared plus 1. The derivative of the inverse cotangent of x is equal to negative 1 divided by x squared plus 1. The derivative of the inverse secant of x is equal to 1 divided by the absolute value of x times the square root of x squared minus 1. And the derivative of the inverse cosecant of x is equal to negative 1 divided by the absolute value of x times the square root of x squared minus 1. So as you can see in this video, I grouped each of the derivatives by how similar they were with their derivative proofs. I did the same thing for the derivative of the regular trig functions, and I hope that that was very helpful in matching the patterns between the derivatives. Alright, well, thank you guys for watching. I hope that this video was helpful and that you either got a nice refresher or you learned where the derivatives of the inverse trig functions come from. Be sure to comment down below what you want to see in future videos, and until then, I'll see you in the next one.